started.
Okay, so first things first, the review is online. Do it. Follow the instructions. Pretty much all I have to say about that, I guess. So, how it works, I pretty much gave you some advice on how you want to look at some past finals and practice some problems. So I provide a link to the finals and the list of problems that you should do and how you should do them, etc. So go there and make sure you do the review. That's it. That will prepare you for the first test, which is next Wednesday, a week from today. So it's on the class website. So the main page where you find the syllabus and the answers to the quizzes and all that stuff. I added a section called Review for Test 1, and you should read that right there. Okay. I also gave you instructions, so make sure you follow the instructions. Okay. As for that, I believe there's nothing much to say because I say a lot. Like I wrote a lot of instructions here, so I'm not really going to say anything other than that. Just I want you to be aware that it's currently up, and pretty much starting tonight, you should try to review it. Because I even put some time, how much time certain things should take you, and just doing that, not counting the review and the reassessing and whether or not you're seeing tutors, just counting the things that I told you, it's like 8 hours worth of studying already. So get started now, you have a week. So pretty much when you start factoring in actually seeing a tutor or seeing me or getting advice from someone or looking up solutions or any of that, it'll start to go into in excess of 8 hours worth of studying. But if you actually get through it according to the instructions, by the time you get to the end, you should be in very good shape. And the format of the finals have changed recently. So, like I said, it used to be something, and you'll see this when you start looking them up. It used to be something like there were 4 sections with 6 problems, and you would choose 5 out of 6. And so, roughly, you do 20 problems in 2 hours and 15 minutes. Now it's more like you don't choose anything; you do all the problems, and you list like 21, somewhere between 21 and 22 problems, and just like do everything, right? So you don't really have that choice anymore. So our test is going to model that, and based on the amount of time that you have per question, I would say our test, it'll be the entire, I still haven't written it yet, but I'm pretty sure at minimum these guidelines will be true. It'll take the entire period, which means it's going to be something that I'm writing for you to be able to do in an hour and 40 minutes, and based on that scale, you can expect around 15 problems. And I think that works out. Because you should be spending roughly, and this is important information, I also mentioned this in the review, important information for you to know is that you should be spending roughly 6.5 minutes on each problem, right? And so with that time limit, 15 questions should take you an hour and 37.5 minutes. So I'm just like, I'm a nice guy, so I give you an hour and 40 minutes. So yeah, I'm just gonna, 15 problems, do everything, that's gonna be test 1. And in terms of what the problems are gonna look like, they're gonna look like the guys that are here. Okay. Any other questions? Yeah.
We leave after we're done with it.
Yeah, it's the entire period. There's nothing to do after. So you just come in, starting at 6. We're gonna do the test. I'm gonna give you the entire class time. If you finish early, you leave. We're not doing anything else. Other questions about the test?
So the
questions are like similar to the quiz questions, whereas like one question has like a few questions within them?
No, the questions are going to look like the review problems.
Okay.
Yeah. Well, yes, it would look similar to the quiz, but the quiz is testing you in a different kind of way. It's like, so you know, like how on the quiz where I would ask that one question where I had to find 4 different equations of a line. Like one problem here would just ask you to find one of those, for example. So it'll be kind of like a quiz, but more kind of focused. Typically, each problem doesn't have a bunch of parts. Some have like 2 parts or 3 parts, but it's not typical. Usually they just test you on one thing. Solve this equation, solve this inequality, do this, do that, find this line, and then they're kind of done. But again, you'll see how the problems are by the end of it. Other questions? Yeah?
Will there be bonuses or is this a straight 15?
I'll put a bonus. So the thing we would talk about next, so something like dividing polynomials. So we're going to look at something like long division of polynomials. That would be the next topic, and maybe exponential equations. Exponentials, functions, and equations. Just some basic questions on this. And we should be able to cover everything, but I guess maybe I might throw in anything not covered in syllabus. So sometimes when I'm guessing where test 1 should end up, it's not always perfect. By the end of the semester, we'll finish everything, but sometimes to make sure we finish all those topics for test 1, we might miss 1 or 2 topics. So if I miss 1 or 2 topics, I'll push them down into the bonus. But the test kind of goes all the way up to functions and being able to graph them and find inverses. So hopefully we'll finish that day or by Monday. But again, it's all kind of review from Math 190, so should be in good shape. Once you get the practice down, it should be in good shape. Other than that, I think we can move on. Because like I said, I left a lot of instructions on the review, so I really talk at length about how you want to do it and how you want to look at the problems. So by doing that, you'll get a nice feel for it. For one of the reviews I had you do, that review's problem set itself was 15 problems, and the timing would be an hour and 40 minutes, and you'll see that one. So that's probably a nice way to gauge where you are. I think that was the fall 2010 or something like that. So there's one of the finals where the number of problems I picked out of that one was 15. It's on the nose, and so that's what our test would probably feel kind of like. Yeah, other than that, we are going to continue with functions. And that is, chapter 2, functions. Continued. Last time we spoke about evaluating functions. So let's actually pick up with, I think this is section 2.7 in your book, but we're going to talk about combining functions. Okay, so the idea here is functions can be combined to create new ones. As follows. Okay, so this is assuming that you know how to write down the formula of a function. Right, which in math class, the kind of problems that we're going to tackle are the ones that you can actually write down a formula for. So one, so given functions f of x and g of x with the same domain and coordinate. One, we can add them. So we do have notation for that, f plus g of x. We can also talk about f minus g of x. And you simply do this by adding their formulas together. It's f of x plus g of x. Or here, f of x minus g of x. So you add them together, combine like terms. Remember, we spoke about this last time. You're subtracting something, that guy should be in parentheses so that you can apply the distributive law. So we spoke about adding terms earlier, so you just pretty much add the terms as in the formulas. Do you want me to give any examples of that? Let's. I'll give some examples later. Right now, let's just define the operations. So addition is an operation that you can do on functions. Two, we can multiply them. So you can have a function that we call fg of x, and this is simply that formula times that formula. And again, in practice, you want these guys in parentheses in case anything that needs to be distributed gets distributed. 3. We can divide them. There's usually one caveat here. So this notation is f over g of x. We think of this as f of x divided by g of x. We'll learn how to simplify that in chapter 3, which is the very first section after our test 1 set of topics. The caveat here is that your g cannot be 0. You never divide by 0. And again, this probably won't be complicated at all, but just so we leave no stone unturned here, f of x is equal to x squared plus 5x equals 6. G of x is equal to x squared plus 4. Find following operation that is going to be really important. But these tend to be not so bad, based on what we've covered already. So, no surprise here. A, what would f plus g of x look like? According to the formula, that's f of x plus g of x. F of x is x squared plus so you have that. Right, this plus that, and then now you just combine like terms. And so x squared plus x squared, 2x squared, 5x, there's no x over there, so that's 5x, 6 minus 4 plus 2. Minus g of x, this is part B. That'll be f of x minus g of x. that'll be x squared plus 5x plus 6 minus x squared minus 4, parentheses, common mistake here. Alright, so now you distribute, and so this would become minus x squared plus 4 after distributing. And so now we have x squared minus x squared, those die, we just have a 5x. And then we have plus 6 plus 4, that's plus 10. Let's see. Fg of x equals f of x times g of x. This is equal to x squared plus 5x plus 6 times x squared minus 4. For some reason, again, it's one of those things that are not really explainable, but students tend to forget the first pair of brackets with something like this. Okay, so remember that. They usually remember the second set, I don't know why, but that's a thing. Okay, make sure both parentheses are important, but this is the first set is a very common one to forget for some reason. How do we actually do that one? Yeah, distribute. How? Someone tell me what we get here. Come again?
I'm sorry. You want to factor that?
No, I want to expand. How do we multiply something like that out?
So it would be 2x to the 4th.
Why would you have 2x to the 4th? What is the rule here? How do we actually distribute something?
You would have to distribute.
Huh? What's the rule? If you were to explain to me in a phrase how you distribute something, what would you say?
Take one turn, distribute seven.
Come again?
Take one turn at a time. Distribute seven
Take one term where?
at a time.
At the top? What do you mean
No,
at the top?
at a time.
Oh, one term at a time? Okay, so where is that one term?
So
Sorry, this one?
for example,
Yeah.
it'll be x to the fourth
Mm-hmm.
minus 4x squared.
Right, so you take this one, take each term in one set of parentheses, and you multiply out the other set. Right, so that you would get x to the 4th minus 4x squared. Then you repeat, right? You take this term and multiply out. So that would give you 5x cubed minus 20x. Then you take the 6 and you multiply out. So that would give us 6x squared minus 24. Right? And then now you combine like terms. So in terms of the 4th power, there's only one of them, so that's x to the 4th. In terms of the 2nd power, notice here I have minus 4x squared plus 6x squared. That gives us plus 2x squared. In terms of the cube power, I only have 1. So that takes care of that guy. In terms of the x's, I only also have 1 minus 20x. And in terms of the constants, I also have 1. That's 24. So that would be the answer. F divided by g, formula says this is f of x over g of x. This would mean, well, you just take the first one, x squared plus 5x plus 6 divided by x squared plus 4. And notice that this works for x not equal to plus 4 minus 2, because that would make the denominator 0. Now let's talk about composition of functions. Yes.
If D was on an exam, you wouldn't have to simplify and then,
D,
yeah. Because if we simplify that,
you could simplify, sure.
then that, do you care?
It depends on the question, probably not. The one thing you want to be careful of when it comes to simplifying is you want to realize, and we'll probably talk about this a little bit more, is that simplifying won't fix the domain. So this we can actually factor, right?
Yeah.
X plus 2, x plus 3. This we can write as x plus 2, x minus 2. This will cancel, and you can think of it as x plus 3 over x minus 2, right? But I want you to realize that while looking at this, you know that x obviously can't be 2. It still can't be minus 2 as well, right? So this would stay. Right? So simplifying doesn't mean that you've gotten rid of the division by 0, right? This is just bringing it into a nicer form for some future computation, but the actual function had a division where 2 points were off, so you have to be aware of that. So one thing, when it comes to simplifying, you have to be aware that simplifying doesn't fix the domain. Right? Probably talk a little bit more about that when graphing, but maybe not. Composition of functions, right? So this, how do I want to describe this? Another important is composing functions and definition. Given f of x and g of x, we define f composed with g, aka f of g, by. So a composition of functions is just plugging one function into the other, and I'm going to talk a little bit about what that actually means. So we can define the function composition f of g, or f composed with g, by this notation. Right, so you see a f, you see a little circle, that's supposed to be a little circle of g of x, and it is defined as taking f and evaluating it at the output of g. And not something you always have to worry about here in pre-calc, but you can know behind the scenes, I guess, that your G would have domain A, output B, where this would have domain B and codomain C. Because the idea behind a function composition is essentially to cut out the middleman. So basically, what this function does is shorten the chain of functions. So sometimes you have rules that you set up that will interact with other rules, and where one function leaves off, another one picks up the slack and then does something else. So for example, what if I only have composing two functions, what that means is that here I have three sets over here, set A, B, and C. And G is a function with this set is its domain, that's its range, so its job is to connect things here in that special way that functions work. So if you take some guy here, which we can call x, G is going to take that to some point, some guy here that we call g of x. And now, if you think of f as a function that goes from here to there, f is going to take this guy and then move him to someone else, and that guy is going to be f of g of x. Right? So one function does something, and then the other function takes that as the input and does something else, right? So you have this chain of functions. G passes the buck to f, and f brings it all the way over here. Now, what the f of g function is basically writing that down not as two formulas in succession, but as one formula that goes all the way from here to all the way there. This is the function f of g. So f of g cuts out the middleman. And with two functions, the use of such a function might not be totally apparent, but then when you start to realize that you can actually extend this process, something like, maybe we had something like this situation. One function did this, and then another one did that, and then another one did that, and then another one did that, right? So I can have the first function, the second function, the third function, the fourth function, right? But here I have to go through like 4 definitions to figure out what the end goal is going to be. Sometimes you don't have that kind of time. Ain't nobody got time for that. So what you do is you develop one function that goes all the way from the beginning to the end, and that function is called the composition. In this case, the composition would be f4 of f3 of f2 of f1. Right? So the point of the composition function is to cut out the middleman. That's how you can think of it. It's a function that combines a bunch of functions that work in a chain. And so in the case that you only have 2, you get some guy that looks like this, f of g. And figuring out a formula for that guy is like figuring out a formula that goes all the way from the first set of things to the very last set of things and eliminates you having to worry about what happens in the middle. Now, in terms of calculations, right, the actual thing that you write down on paper and work out, function composition is done by evaluating one function at the output of the first. And it kind of goes in reverse order, as you might have noticed here. The first function for us is going to be the one to the right. So even though you're reading it left to right, really the first guy to happen was the guy all the way to the right. Then this guy happened, then that guy happened, then that guy happened. So you're thinking of this guy doing something, you plugged it into that, and then that did something, then you plug it into that, then that did something, you plug it into that. And then what's the rule for this entire operation in one quick sentence? Well, it's the composition function. So let's do some examples of that. And then we'll talk about the difference quotient. Very important. Under raising examples. Again, I'm going to use 2 functions and we're going to do some compositions here. Those. Make sure to remember how to do those. Okay, so there's always a problem like this on a final, and there's always going to be a problem, and therefore there'll be a problem like that on our test, right? They often ask you to find kind of add one here. So sometimes they might write something like this. F G of 2 minus F of 3. Right, so they'll define a couple functions and then they'll give you an expression like this and ask you, what is that? Let's go to A. Okay, so if I want to find f of g, how do we think of that? Right, so this is f of g of x. And what does that mean?
You plug in g of x into every x value in f of x.
Right. So that's how I like it. Like I said, the connection between math and language is very important. A lot of people overlook it. Normally when there's some sort of operation that I define for you guys, you want to be able to describe it in words, describe it in a very concise sentence. That way you'll never actually get confused. A lot of times when people get confused, or it seems like hieroglyphics, is because they don't assimilate the mathematical terminology into their normal everyday language. And so when you see that, what you want to think is replace every x in f of x with g of x. Right? So that's what you want to think when you see something like that. Right? And so immediately what you're going to realize is that that means you're pretty much going to copy this down, but instead of writing x in all these positions, you're going to write g, right? So in your head, now you're seeing this. Right? Even though you might not write that down on the paper, that's what you should be thinking, right? Whatever goes in the parentheses replaces all the x's in that guy. So we did that time, like, even if I throw a smiley face in here, it doesn't matter. What that means is you go to this guy immediately to the left, and every instance of x, you replace it with whatever is in those parentheses. Okay, so in this case, that's going to look like, well, 2 times 2x plus 1. This plus 3 times that plus 1. Okay. So I'm literally, every x, I just imagine there's a void there, and now I'm dropping into that void the g of x. Let's say I wanted to expand and regroup here. Being able to do that kind of thing is going to be important for the next thing I'm going to talk about. So let's actually worry about how would I expand this? How do we continue?
You would address the exponent first.
Address the exponent first. Okay, so 2, what does that become?
4x squared plus 4x plus 1.
Right? Plus?
6x plus 3 plus 1. 8x squared plus 8x plus 2.
What do we have now?
8x squared plus 14x.
Okay, 8x squared, there's only 1x squared. There's 8x plus 6x, that's 14x.
Plus 6.
Plus
And we have 2 plus 3 plus 1, that's 6. So that's going to be it. So if you were asked to find and simplify f of g, that would be your answer right here. And as is often the case with the composition problems, the battle is won or lost literally on the first step. The first step is where a lot of people always mess up. So make sure you get this idea down. Make sure you get this language in your head. That's the important part. Knowing this is more important than knowing this particular example. Okay? So don't pay attention to these numbers or what the functions look like. Pay attention to the idea I'm applying. students take tests and they're like, well, this test was nothing like what you did in class. That is very rarely the case. Usually what happens is they paid attention to the particular kind of thing. Like he would put a square here, but in the test he put a cube, and then it looks really different, but it's not different. It's exactly the same idea. Right? So pay attention to the reasoning behind the problem. Right? The particular example is less important. Like if I threw in a square root here on the test, it shouldn't throw you. Right? It's not going to be any different. Right? What? You never did one with a square root before. It doesn't matter what I did it with. Replace every x in one function with whatever I wrote down here. That will always be the case. Okay. B, g of x, g of f. Okay. So anytime you see that g with a little circle here, that means this, right? And when you see that, what do you think? Replace every x in g with f of x. That means you're thinking 2f plus 1. That means you're thinking 2 times 2x squared plus 3x plus 1 plus 1. C, just apply the distributive law there. That'll be 4x squared plus 6x plus 4 plus 1. But it's not C. Continue B. 4x squared plus 6x plus 5. Huh? I multiplied by 2. Yes. Okay, C. Okay, what is this one? Same as A, okay. Just paying attention whether you're paying attention to the notation. Same as A. Okay, move on. D. What if I have f of g of 1? Okay, so this one, there are 2 ways you can think about it. Either way is fine, just do whichever way you prefer. Some people might prefer one way versus the other. So one way, first find f of g of x, then plug in x equals 1. Now normally I won't have a strong recommendation for this method. I really only recommend you doing this way if you're going to reuse f of g of x multiple times, right? So for a problem you have to find f of g of 3 and then f of g of 7 and then f of g of... In the same problem, if you're reusing the function, it's better to just find the general function. It's going to be easier computationally to plug everything in. So this is recommended only if f of g is being reused in the same problem. Otherwise, I don't necessarily recommend you do it this way. It's just a matter of preference otherwise. So here we saw that f of g of x was, we computed that. What did we get?
8x squared plus 14x plus 6.
So we got, okay. And so this means, right, so if you're doing this from scratch, you would do the calculations we did for part A pretty much, and you'd eventually get to here. And then f of g of 1 just means replace all the x's with 1. So So that's what, 28?
Yep.
The other way, again, not necessarily recommending one way or the other. I'd probably recommend this way if in that situation, but in general, I don't really see one benefit over the other. So the other way is to realize that f of g of 1 means f of g of 1. So what you can do is you can first compute this. Then plug that answer into f. Now either way you'd get the same answer. Let's actually see that. So a couple ways you can think about this one. Again, one not necessarily recommended, except in this one situation I'd probably recommend it. Beyond that, matter of preference. So first we would find g of 1. What does it mean to find g of 1?
Plug in 1.
Right, everywhere I see x, I'm going to plug in 1 into g. So that's 3. And so this means that f of g of 1 is just f of 3. So I'm just going to now plug in 3 into the f. So this is 2 times 3 squared plus 3 times 3 plus 1. Okay, so 3 squared is 9 times 2, that's 18 plus 9 plus 1. That's 18 plus 10, 28. So you get the same answer. Let's look at E. So f of g 2 minus f of 3. So again, kind of the same idea I do here. You could find the general formula for this and then plug in 2, or you can find g of 2 and then plug that into f. Either way, you would have here f of g of 2 just means 2 times g of 2 squared plus 3 times g of 2 plus 1 minus parentheses, kind of running out of space here, f of 3, which we actually computed here, but I'm writing down 2 times 3 squared plus 3 times 3 plus 1 parentheses. This is going to be, well, g of 2 I know is 5, so this is 2 times 5 squared plus 3 times 5 plus 1 minus 28 in parentheses. We're on that. So this is going to be 25 times 2 plus 15 plus 1. So what is that?
66.
That's 66 minus 28. And you would get what?
38.
Yeah, so there'll be a problem where you have to do something like this, right? They're going to give you a couple functions. Oh, find this composition, evaluate it at this point. Any questions on this? Okay, now we're going to talk about some important compositions. Why are they important? You'll see it in Calc 1. It's not our discussion at this moment. Just know what these are and that they're important and that you need to know how to compute them. The why will be explained in Calculus 1, so I don't want to steal your Calc 1 professor's thunder here. Do you guys know what this is about? And everyone's, yeah, we were in Joan's class. Damn it. That ruins his entire speech where he was going to get all excited explaining it. They're kind of a big deal, but let's... Does anyone know what I'm going to talk about? I think some of you probably already know. The difference quotient. Groan. Yeah. That's students just start groaning, and professors get all excited. Oh my god! But the reason why math people get excited on this is because the difference quotient actually the basis of literally half of calculus. Calculus is pretty much the study of two things. One of them, we figured out how to solve that problem through this guy. So that's why it's important. Like, the difference quotient is responsible for half of his time being there. So he's going to get excited. Oh, it's a difference quotient. Right? This is why we're here. Yeah. Okay, so let's actually look at that. So for a function, now the phrase the difference quotient should actually mean something to you, so I might not mention the formula for it specifically. It's one of those things where saying that phrase should make you think of the formula. Definition. For a function f, its difference quotient is f of x plus h minus f of x all over h. So if I give you a function and say, find the difference quotient, you need to evaluate this expression. That's what that question means. So that is called the difference quotient, a very important expression. Notice that it is just a formula that is a combination of a composed function, f composed with x plus h, minus f of x all over h. Often phrase, the average rate of change, tells you pretty much how the y value changes on average on some interval. And however, in that situation, we normally use a slightly different notation that's kind of easier to manage. That version of the formula. It's exactly the same thing. I can tell you essentially what you can do is you can think of A as x and set B equals x plus h. And what you'll have is that when thinking of average rate of change over there, a different notation is used, namely f of b minus f of a over e minus a. That's also an important one to know. So they tend to call this the average rate of change formula. But it's just the difference quotient itself. It's literally just a relabeling of the same idea. thinking, should I steal any thunder? Here's kind of what's going on. So let's say there's one point you know here, if you label that x, there's another point you know over here, but you kind of think of it as being just h units from the point you care about, which is x, so therefore this x value would be x plus h. The corresponding y value over here is f of x, the corresponding y value over here is f of x plus h. And basically you just imagine a line connecting these 2 points, and then the slope of that line called the secant line is the difference quotient. Right? y2 minus y1 over x2 minus x1, you get that. Right? You might say, well, that's it? That's so important to calculus? Yeah, it's super important to calculus, pretty much. Half of calculus is built up on us being able to find the slope of a straight line. Again, complicated things always come from simple things. Now, you can think of exactly the same interpretation, but with different labels. Call this first point A, call that second point B. This would be f of A, this would be f of B. Again, imagine there's a line connecting these 2 points. It will be called a secant line, and again, find the slope of that line. y2 minus y1 over x2 minus x1, you get that form. Right? So the difference quotient and the average rate of change formula, they're exactly the same. It's just a change in notation. You tend to want to think of it this way as opposed to this way, because this formula, if you want to compute an average rate of change, this formula requires you to know the difference between the 2 points that you care about, but you can find that usually by subtracting one from another. So it's more explicit in this version of the formula. And so, yeah, they're both difference quotients. But usually when you refer to difference quotient, people tend to be thinking about this one. When they refer to average rate of change, they tend to be thinking about that one. But they're, of course, the same thing. So that's where the expression comes from. Why it's important for calculus, I'll let your calculus professor talk to you about that. For now, let's... And if he tells you this, pretend to be excited. Oh, wow, that's so cool, Professor. I never saw that before. It'll make him feel good. Okay. Nothing really much more to say. What you do need to know is how to actually compute this expression. So let's look at a few examples here. Want to go through all of these? Yes. Okay. Let's do the first one, example. If f of x equals find its average rate of change on the interval -1 to 2. Another way to make that statement, that same statement, is you can say or for x equals -1 to x equals 2. Or they can say for your x values between -1 and 2. These are all exactly the same thing. So you can say on this interval, or between these two x values, or for this inequality, right? So they'll give you a function, they say find the average rate of change, here are your endpoints, and pretty much that means you're going to use this. Where in this case, the A is always the first endpoint, the guy on the left, the B is always the second endpoint, the guy on the right. So here, A equals -1, here B equals 2. This means the average rate of change is f of b minus f of a over b minus a. F of b, that just means f of 2 minus f of -1 over 2 minus -1. Okay, and what is f of 2?
Two times 2 squared plus 1. 9.
Minus, what is f of -1?
2 times -1 squared plus 1. Which is 3.
Over?
Over 3.
Over 3. Anything missing here? Take up the red talk, everyone knows what I'm going to do. Parentheses. So, it might be something that you have to distribute. You'll see it later. But here you can first compute the number in here, which you know is going to be 3, and then you don't have to worry too much about the parentheses. Computing this here, 2 squared is 4, times 2 is 8, plus 1 is 9, so that's going to be 9. So pretty much you'll have 9 minus 3 over 3, which is 2, right? That's the average rate of change. In other words, the fact that this is a plus 2, you can kind of interpret that to say, on average, every time the x value increases by 1, the y value will increase by 2, right? If this was a -2, the interpretation would be, every time the x value increases by 1, the y value decreases by 2. That's how you can think of it. I won't write that down. I don't think that's actually knowledge you'll ever actually use in this class, so I'll just say that. And one day you'll remember I said it, and you're like, oh, that's what he was talking about. Hopefully. So that's an average rate of change. Way too aggressive. 2. Find the difference quotient of f of x if a. We're going to do a few here because this one is actually important for you to be able to compute well. Those 5. Something I forgot to mention because I saw this on one of the finals. So maybe I should just mention that. In general, it's not really something I care about. But the top part of the difference quotient, you might see this referred to as the net change of the function. So if you see in a final, it asks you to find the net change of this function. It's just the top part. Okay. So we're going to get through these problems. Technically, we have all the skills to do these already, so let's just go through it really quickly here. You guys can tell me what to write. So what's the difference quotient for f of x? Well, it's f of x plus h minus f of x over h. Okay, what does that look like for this function?
plus h squared minus squared over h.
That's right. Again, a common mistake here would be someone would write x squared plus h. Wrong. F of x plus h means everywhere you see an x, you replace it with x plus h. So you get this. Every now and then I also see students keep writing the f here. That's also wrong. This is what you should have. That's the first step. Now, usually 70–80% of the time, once the student gets the first step, they actually complete the problem correctly. The mistake, if they get this wrong, chances are they got it wrong on the very first step. So be careful that you're really thinking about what it means to take a composite function. How would you continue here? What next?
It's gonna be x squared plus 2xh plus h squared minus over h.
Okay, now what?
X squared on top.
Okay, again, common mistake usually happens here. Students will just say x squared plus h squared, and they forget the 2xh part. But once they get this, they usually know better than doing that. So that maybe happens 30% of the time. So chances are if you get this first step, you'll probably know this step as well. But again, look out for that. Make sure you know you have to expand using that formula or FOIL it out. What happens now? Right, the x squares kill each other. Here we have the 2x plus h, 2xh plus h squared. Common mistake here would be to cancel h. You cannot cancel across sums. The next step, therefore, would be to actually factor out the h. So 2x plus h would be your answer. So this is one of the problems where you kind of, once you can set it up correctly, it's kind of like follow your nose. You realize that once you figure out the things that you're not supposed to do, the thing you're supposed to do kind of becomes obvious. So you're like, here, you can't cancel the h. So you're like, what can I do if I have to simplify this? Well, probably expanding that square would be a good idea. There's not much else you can do here. And remember, I mentioned this before, but an important thing in simplifying this is to actually cancel the denominator. So if you're finding a difference quotient in this version, you are not done simplifying until you cancel that denominator. So that's always our goal. You need to cancel that h. Right? So the problem is done once I cancel that h. Right? Until you cancel that h, you're not done. So once they say find and simplify the difference quotient, you are going to realize that you're looking for this expression, plug in correctly, and you keep going until that h gets cancelled. Okay, let's look at B. So difference quotient is f of x plus h minus f of x over h. What does that look like in this case? Yeah, Ian?
X plus h.
Notice that the x plus h is all under the square root. It's not square root of x plus h separately, right? Because I'm replacing the x with x plus h.
Minus square root x over h. I think you just leave it like that.
What?
You leave it like that. You can't really do anything to it.
Are you joking? Are you messing with me? She's messing. Yeah, she's always messing with me. Okay, what would you do? Seriously. Yeah?
Wouldn't you multiply with the one that will complete the square?
Complete the square is not the right
I mean,
phrase.
Conjugate?
Difference of squares, conjugate. Conjugate is what you would do next. So you would multiply and divide x plus h plus radical x over x plus h plus radical x. So that means the top would now look like a minus b times a plus b, which we now know becomes a squared minus b squared. So it's this squared minus this squared all over h x plus h. Okay, now what happens?
The x cancels out on top.
The x kills each other.
Cancel out the h.
Right, so now you have h over h times x plus h plus x. H's can cancel, right? Now you know we can leave it there, right? You keep going until the h is canceled. So until that h is canceled, you're not done. 1 over x plus h plus square root of x. That's going to be the answer. Just, let's see, how would this, like if I'm doing, okay, so let's say this problem was worth like 6 points, which is roughly what the problems are going to be worth on your test. Okay, so like the first step is always the most difficult one, it turns out. So just to give you an idea of what to expect here, like you get that first step, and I'll give you like 3 out of 6 right away. Right? The next 3 points comes from you being able to simplify correctly. Okay. So you can do that. I will be very happy. But still, we'd both be happier if you could finish. Let's actually move on here. Let's see.
Oh, yeah.
So again, we're computing the difference quotient. So that is f of x plus h minus f of x all over h. I keep writing down the formula until you memorize it, so that's why I keep writing down the formula, because it's kind of how I expect you guys to write things down, how I expect you guys, when you're practicing, to write things out. Another question I get all the time, students always ask me, so how do you expect us to like write this out? Because you know, on quizzes you only expect the answer, but on a test you expect us to show work. Like, what do I have to show? Exactly what I'm writing on the board is what I expect you to show. Okay, so in this case, what is that going to look like? We're doing C now.
1 over x plus h minus 1x 1 over h.
Right. You could put this parentheses, but there's only one term, so it's not that important. Again, x plus h is all in the denominator here. Okay. So now what? Common denominator, right? Find the LCD. In this case, what is that?
X plus h times x
Times x. Not h. Technically, the h here, you would think of the h as its own fraction. Right? So you wouldn't think of the h as the denominator. Right? So you have 2 fractions in the numerator divided by 1 fraction here. So the denominators are x, x plus h, and 1. And so the LCD is going to be x times x plus h. And we know how to simplify complex fractions. You multiply and divide by the LCD. So now what you're going to do is this gets distributed, and then this just multiplies straight across. And so this times this, the x plus h's will cancel. You'll be left with an x minus this times this, the x's would cancel. You'd be left with an x plus h. Common error here is to forget the parentheses. So parentheses should be there. And then you just multiply directly across. I mentioned this before, but when you want to simplify a fraction, you never expand the denominator. Expanding the numerator is necessary sometimes, denominator, never expand. You always want to keep that factored, and you always want to factor it more if possible. Let me just mention that here. Never expand denominator. I'm pretty sure I mentioned this at some point, but let me just remind you of that. Okay, so now where would we end up?
The x cancels out on top.
Right, so I have x minus x, so the x's are going to go away.
Negative h.
And on top now I just have negative h over h, x plus h. H is cancelled, now we're done. That's the answer.
Wait, you flipped the reciprocal. What did you do there?
I multiplied and divide by the LCD.
No, under that, the second to last step. Where you said
Nothing.
never.
I distribute this and I
No.
got that.
I said where you wrote never expand denominator. Can you do that part again? Because I got it.
Oh, I didn't do it because I said never do it, so I didn't do anything. I'm saying there are some students who they sometimes get the urge to actually multiply this out and say like h x squared plus h squared x or something like that. They'd expand the parentheses. I'm saying don't do that. So I didn't do anything. I'm just saying that if you're thinking of doing it, don't. So here, multiply and divide by the LCD, I get this right away, and ultimately I get to cancel the h. Now, D. So we're looking for the difference quotient, that is f of x plus h minus f of x over h. What does that look like here?
One plus.
Someone else. Like it's Taisha and Francisco. Yeah,
Can't you just plug it into x?
sure. Like, what would I write?
1 plus x minus 2x squared,
1 plus x minus,
2x squared
yeah,
plus h
then
minus 1 plus x minus 2x squared over h.
do we agree?
No,
No. What happened?
parentheses.
Parentheses. Oh, yeah, parentheses. Okay, great. Now it's fine.
No,
What's the problem?
the others are parentheses.
She's like, every time he stops and asks what's wrong, it's always parentheses. So I'm just going to keep saying parentheses. No. What's the issue?
You should put x plus h instead of x.
You should have
X plus h instead of x.
Yeah.
where?
Like each x instead of x, go x plus h.
Okay, right. So again, the
One-
common mistake I mentioned here. What does that mean? You look at the function f, every single position in which you find an x, which is here and here, you're going to replace that x with x plus h. So what this is this is f of x plus h separately. You understand? It's not the same as f of x plus h. Right? So that's the common mistake I'm talking about. So I'm not picking on him or anything. I'm saying like it happens. Right? Like I see this all the time. So you really have to understand. Just because you're doing a larger difference quotient, you need to actually remember what each part means individually, right? So you have to worry about f of x plus h, worry about f of x, worry about h. What this means is that there's an x plus h in the parentheses. It must literally replace every instance of x in the original. So that is not correct. And so what happens is, again, we think of the function as just a template, so that's 1 plus, there's something here, minus 2 times that thing squared, minus, here I copy the function, and then I just make sure that that x I replace with x plus h, replace with x plus h. So that's the correct first step. All of h. Okay, so knowing that that's the first step, which at this point I'll give you like half the credit for doing this step, because like I said, students commonly mess up that first step. What is the, how do we continue? This one? Okay, and what would you get? Huh?
It'll be x squared
X squared
plus 2xh
plus 2xh
plus h squared
plus h squared minus x plus 2x squared all over h. And so now what?
1 plus x
Yeah.
plus h minus 2x squared plus 4xh.
This is a
No,
plus-
minus, sorry.
Right, so minus
4xh minus 2h squared.
and just copy that back. And now what happens?
Combine like
Right, combine like terms. So what happens?
2x squared gets
Well, 1 minus 1, x minus x, minus 2x squared plus 2x squared. That's it. So we're left with an h.
minus 4xh minus 2h squared over h.
Minus 2h squared over h. Now I can cancel these, right?
no.
No, can't cancel across sums. So what do we do?
Factor.
Factor out the common h. That cancels. That guy cancels. That means we're done. So now I'm just going to write this a little bit cleaner, what's left over. So that's the difference quotient. Any questions on this one? Be very careful with the composition of functions. Right? Saying a function of something, this means everywhere you see x in the original, replace it with the something. Okay, last one. We're doing a lot of examples on this one, but it's a guaranteed problem to come up now and in Calc 1. We're going to be doing it all the time, so I feel like it's worth a lot of examples. So I'll throw you guys in different situations and see if you know how to handle it. So here the guys, f of x plus h minus f of x over h. In this case, what do we get? Yeah?
It's just gonna be 2x plus h
Like that?
plus 1 over x plus h minus 2x over plus 1 over x over h. Then parentheses.
Where are the parentheses?
Like the first part and the second, so
Where?
in front of the 2.
In front of the two?
Yeah.
Like that?
Mm-hmm. And
Like
then,
that?
no, then you put the second one after the 1 over x plus h.
Between the x plus.
Like here?
No. Alright, so
Just literally read from left to right and tell me when the parentheses should come up.
so
two.
one set of parentheses is going to go in front of the 2x plus h. You put one parentheses open.
Here?
In front of the two.
In front of the two?
No,
Okay.
in front of the-
No.
Yeah, never mind. I can't. I'm confused.
Huh?
Two
You mean
parentheses
after
x plus h.
Huh?
After
2 parentheses x plus h. Right? That's correct.
Yeah.
Do you see why?
Yeah,
You see why?
I got it.
Yeah. Okay. So it comes after that. And why? Again, it's because when we look at this, we kind of imagine that. Right? So that was last class I mentioned that, right? So pretty much everywhere there's an x, you imagine that there's a void there. Right? And once you have like f of blah, whatever is in the parentheses here, you just drop in the void. Right? So the x plus h jumps in here, the x plus h jumps in here. Right? So the parentheses would go after the 2. And yes, because there's a negative sign here and I'm subtracting 2 terms, I need parentheses right after the minus sign. So that's the correct first step. So what would you do now? Distribute this, you get 2x plus 2h plus 1 over x plus h minus 2x minus 1 over x h. What can we do here? Two x's would go away, 2x minus 2x. And so how do you deal with that?
Most common denominator.
Okay, it's just gonna be
X.
x times x plus h. One thing I would do here is that, so we know about those techniques, right? So if there are radicals there, you might want to multiply and divide by the conjugate. If there's a complex fraction, you want to multiply and divide by the LCD, et cetera, et cetera. But notice here that the multiplying and dividing by the LCD, the only reason I need that technique is because of these two guys, right? Notice that that guy isn't a problem, right? So one thing you can do here in this case is like you can separate guys that require different techniques, right? In the sense that you can separate the fractions, right? Because I can split a fraction across the numerator, right? So I can think of this as 2h over h plus do you see why? So we see why that's true. Now why I would do that here is because, it's not because like if you immediately multiply by the LCD and divide by the LCD you get something wrong. It's just you're going to need more calculations now. Because now you're going to take an x times x plus h and multiply this guy, which you're now going to end up having to distribute, as opposed to just, let's not worry about it. You know? So I'd probably split these up so you can apply different techniques to different parts. And for this part here, I'm going to multiply by x times x plus h over x times x plus h. So now I'm just bringing this 2 along with me while I'm simplifying the other part. And so here the x plus h's would cancel. I get x. Well, we did a similar guide to this before. Plus h all over h x plus h. Here the x's would die. So we have 2 plus minus h over h x times x plus h. H's cancel. Now notice that all the original h's in the denominator are canceled. I canceled one of them over here, and I just canceled this one. That means we're done. So this would be 2 minus 1 over x times x plus h. Let me quickly show you what the other option would have looked like, so star. So it's not that you'll get the wrong thing. It can be a little bit more annoying though, and I've seen students just like, their brains just give up in the middle of all the annoyance. That happens, and you want to kind of guard against that whenever possible, right? Sometimes you'll know what you're doing, but you're in a test and then something just gets more long and complicated to the point where, oh man, right? That's when you start giving up, you start getting sloppy, you start forgetting parentheses. So pretty much the idea is, if you want to apply some special technique, try to figure out a way to only apply it to the part of the thing that you're looking at that needs it. This is not a particularly difficult case to deal with, but let me just show you an example of what it would look like had we not done it, or picking up from star. We would have, okay, 2h plus 1 over x plus h minus 1 over x all over h. Let's say right away we multiply and divide by the LCD because we know that's what we should do. Notice what's going to happen here is now you're going to have this times that, 2xh times x plus h, plus this times that, you'll have x, minus this times that, you have x plus h, over h times x plus h. Now, not terribly annoying because of this particular example is easier, right? If I had a 2x squared instead of a 2x, it'll immediately become a lot more annoying, right? It doesn't take a lot to make it more annoying. But here you can appreciate, now I have to deal with something like this, as opposed to just writing a 2, right? But you can still get through it if you're great at algebra and you're into that sort of thing. So we'll expand here. So 2x squared h plus 2xh squared. And here the x's will kill each other. We have a minus h. And at this point, what can we do? Well, we want to cancel the h, so I factor out the common h. And I would have 2x squared plus 2xh minus 1 over hx plus h. Now the h's cancel, so I'll get this answer. 2x squared plus 2xh minus 1 over x times x plus h. Is that the same as what we had, by the way? Well, it is. What we could do is split these two up. And here, 2x is a common term. I can factor that out. And I would get x plus h over x times x plus h, right? This will cancel that, the x's will cancel, and you just get that 2 standing by its lonesome, which is what we had here. I think we'll stop there. So on Monday, the plan is to get into, yeah, I think we've got 3 minutes left, but that's not enough time to talk about. So Monday, we will talk about the main things I want to cover is drafting and maybe inverses, and I think that's the last 2 things you actually do for the test. But again, I think you guys will probably be good enough to actually start practicing those right away. So we'll stop there.
Professor, give me back the quizzes.